In regular classes, I like to introduce the quadratic formula, get to that, by using an example, a specific example that results in a quadratic equation which we cannot solve by either factoring or by using that square root method. And so it revolves around what's called the golden rectangle. So if you take an introduction to arts class, for example, you might run across this term, the golden mean or the golden rectangle, because it was used in art and still is used in art occasionally. But it's been used in art and architecture for many, many centuries. So there was in ancient times, and I'm not sure if this originated with the Greeks or with some other culture, but there was this idea that the most perfect, aesthetically pleasing or artistically pleasing rectangle is the golden rectangle. And here's what it is defined as. The golden rectangle is a rectangle such that when you cut off a square from it, the remaining rectangle over here has the same proportion as the original. And so let me run that through again. This rectangle, golden rectangle, and I'm not sure where that name came from, but nevertheless, that's what it's called. It's a rectangle such that if you cut off a square, the remaining rectangle has the same proportion as the original. So you see this in a lot of ancient architecture, even up to the Middle Ages. It's often used. In art, shows up a lot. Leonardo da Vinci was fascinated by the idea. If you look at the Mona Lisa, I believe that painting, you could frame her head inside of a golden rectangle. Some of the details in the background are use that same thing. Even into the 20th century, artist named Piet Mondrian made a good living drawing rectangles and coloring them in. And sometimes these paintings he used golden rectangles. And if you're familiar with his art, it's very distinctive, and it's just a bunch of lines crisscrossing in a grid, and these boxes are colored in, and that though is considered art. So it's a modern art. All right, well, I want to get to the point of let's figure out what this rectangle is. And this whole side here I'm going to label X. And this side I'm going to label 1. So it turns out that the number X is going to be the number that's called the golden mean. The golden mean is this ratio of that side to that side. By ratio I mean if you take this length and divide by that length, you get the golden mean number. Well, if I were to subtract off or erase a square from this rectangle, then what's left here? Well, this length is what? If it was a length X from front to back, then this remaining part is X minus 1, because I subtracted 1 unit of length from the original side. So the way this works, the ratio of the long side of the original rectangle, long side divided by short side, X divided by 1, is going to be equal to the same ratio from this rectangle. So this long side now is 1, and this side is X minus 1. So these ratios are equal as per the definition. So that leads to an algebra equation. And I'm not clear if that was solved in ancient times. It may have been. I know the Babylonians had a way of, and the Greeks had ways of solving certain kinds of quadratic equations by some methods that you wouldn't recognize out of this course. But there are ways there were ancient ways to solve these. All right, before I erase the rectangle, I'll just point out something else here about these golden rectangles. You do see this sort of thing come up a lot in nature. If I took a golden rectangle and continued to subtract off squares. So this, taking the square from this rectangle, results in this golden rectangle, and subtract the square off there. And if I just keep taking those squares off, if you connect these corners with a spiral, oops, I didn't do that right. It's this corner, that corner, that corner, that corner, that corner, that corner. Okay, those are the corners I meant. If I connect these with a spiral, and I didn't leave quite enough room here to draw all my spiral, you get this sort of shape, and that is the shape inside a nautilus shell. A nautilus shell, I've seen these in museums and gift shops. I'm not sure where these things grow, but they're big. A nautilus shell grows in the ocean, and they can be maybe this big. Well, sometimes these places will take them and run them lengthwise through a bandsaw, so they split open into two equal halves. And you'll see chambers inside of a nautilus shell, and these chambers, as the mollusk inside, I hope that's the right species term for it, as the animal inside grows, it sort of chambers itself off and continues to add to its shell. But anyway, the shape is a spiral, which fits the golden rectangle idea just perfectly, about as perfectly as you could get it out of nature. The Nautilus exercise equipment that you've probably have heard of uses some gearing, which is shaped in this nautilus shape. So that's just one little small area of life where that comes from. All right, well, let's get on with the algebra here. And there are books written about this golden mean, and so there's a lot to it, and it shows up in a lot of places again in nature. All right, now where would you begin on this problem? Well, I want to cancel off the denominator, and so we can do that by multiplying the equation by the common denominator of x minus 1. So on the left I get x times x minus 1. On the right, these cancel and give you 1. So at this point we have, if I expand this out, this is x squared minus x, and if I subtract 1, minus 1 equals to 0. So here's our basic equation that will find the golden mean for us. How do you solve that? Well, you can try factoring, and it won't factor, and it also won't submit itself well to the square root method because here's a term squared, but if I bring this to the right side, it's not a constant number. It still has a variable in it. So we need some other kind of technique for solving this. And what I'm going to do is a technique called completing the square. So I'm going to, first I'm going to rewrite this at the top of the board, this equation. And it was x squared minus x minus 1 equals to 0. So to complete the square is to reorganize this equation into a form where we can use the square root method that you've just learned about. And there's a trick to this. It's not very intuitive. Somebody had to stumble upon this. In general, you first have to make sure this coefficient is 1. Now it already is, but if that was, say, a 2x squared there, then our first step would be to divide everything by that 2. So now I have a 1x squared. So that's always the first step in completing the square, is to make sure your leading coefficient, that's the number multiplying x squared, is equal to 1. It's already done. So next I'm going to take the constant term and shift it to the right side. So I'm going to, in this case, add 1 to both sides. And this gives me x squared minus x. I'm going to leave a space here, equals to positive 1. All right, now the next step is really the completing the square step, and it's the part that's not terribly intuitive. But if you take college algebra, you'll use completing the square to work with circles. And if you take trigonometry, you'll use it again to work with parabolas and hyperbolas and ellipses. It comes in handy in various places in mathematics, this process of completing the square. And here's how it works. I'm going to take half of the coefficient of x. So the linear term is the first power term. The coefficient here is -1. So I'm going to take half of -1, and that would be -1/2. And I'm going to square that number and add it to both sides of the equation. So again, you take half of the coefficient of x, square it, add that to both sides of the equation. I have to add to both sides to keep the equation in balance, and we'll see shortly why we do that. Alright, so this becomes -1/2 quantity squared is +1/4. So I have x squared minus x plus 1/4. And on the right side I've got 1 plus 1/4. So it may not be readily apparent, but if you do complete the square correctly, then the left side is a perfect square, trinomial. You know, this factors as x minus 1/2 times x minus 1/2. Now, we're not used to factoring with fractions like that, but you could verify that. If you multiply this out, you would get that expression on the left side. So the left side factors as a perfect square. By that I mean both these binomial factors are identical. So we could rewrite this as x minus 1/2 all raised to the second power. On the right side, 1 plus 1/4 would be 4/4 plus 1/4, and that would be 5/4. So, what did that accomplish? I have a term squared equal to a constant number. So now we can use the square root method to solve this problem. So I'm going to take the square root of both sides, and there's a plus or minus symbol there. So that eliminates the exponent of 2 on the left side. I have x minus 1/2 equals to plus or minus the square root of 5 over 2. So notice that I was able to simplify the denominator as just an integer. Square root of 4 is just 2. And finally, we'll add 1/2 to both sides. So x would equal to 1/2 plus or minus the square root of 5 over 2. So I just added 1/2 to both sides. And as will just about almost always happen, we have the same denominators here. And so it makes it easy to combine this into a single fraction, and that would be the typical thing to do. So I need to make a little room here. And the answer to the problem is x equals to 1 plus or minus the square root of 5 over 2. So there you go. There's the solution. Now that can be written as two separate answers. X equals to 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. So there's the two separate answers. It turns out this is the golden mean number, because if you work this out, and we're going to look at this with calculators, but if you run this through a calculator, this is approximately 1.618. Oops. 1.618. And this number is negative 0.618. So there we go. The golden mean then is about 1.618. Okay, so there you have it. This is a process is called completing the square. When I was in high school, I learned this stuff over. We had a whole week to drill completing the square. We got good at it because we spent all week doing completing the square. You don't really have that luxury to focus on a little technique like that in college. We have to learn too much too fast. So here's the good news. I want you to see the completing the square. You've seen it now. You don't have to learn it. Not for this course, as far as I'm concerned. because the other method we're going to use to solve is called the quadratic formula method. And it's faster to learn, and so that makes it more practical. If you want to use completing the square to solve problems, I'm perfectly fine with that. I'm as fast using both ways myself because I've did all that practice years ago. But quadratic formula is probably a more practical thing to learn. So anyway, there's completing the square, and we'll move on.